Well, good morning. This is Monday morning, the 17th of July, 2017, 8:04 now in the morning. Math 125, Calculus 1, and we have one student here. Okay, glad she's here, but I don't know where the rest of you are. Hopefully you will be coming in. I think last time we were trying, yeah, here we go. The first part of this chapter, or this section, had very few slides in it, you know, and the one that was in this was a page or so back. But now we're sort of catching up with the slides, or the slides are catching up with us, one of these. And this is example 6 where we left off last time. Any questions before we get going today? Okay, the only announcement I know about, and this is a minor one because I don't think it will affect this class very much, but I do have a doctor's appointment tomorrow morning at 8:20, and that means I have to be at the clinic for labs at 7:20, meaning I will not be on campus at 7:45 in the morning, obviously. My first class is 8 to 9:50 tomorrow morning, so I won't be making that class. But we already made up the class last week, but we went an extra 55 minutes both Tuesday and Thursday last week so that we'd make up for the class I was missing this week. I'm sorry we couldn't have done that with some of the ones I've had to miss in this class, but with 4 classes a day, I don't have enough hours in the week to make up those classes. So anyway, that's water under the bridge or over the dam or somewhere. So anyway, tomorrow, if you come looking for me around 10 o'clock and I'm not here, that just means I'm not back from the doctor's appointment yet. I'm hoping I'll be through and back here by 10, but I can't guarantee it because I can't guarantee how things are going to go at the doctor's office. It's a routine thing, but if he gets behind with other patients, then he may be behind with me too. So I'll get here as soon as I can tomorrow. The one other thing that is going to be happening, not this week, but next week, I believe it is I have a hearing, planning hearing meeting, but that's also on a Tuesday. Pretty sure it's either a Tuesday or Thursday. It's not on a Monday or Wednesday. So I will be, it seems like that one is at 10 o'clock. So that's going to mess up that class again. I don't know if I should go straight to the Birmingham campus for the hearing, or come here and try to teach 30 minutes and then go to the Birmingham campus. It's kind of nuts, so I'll see how things go. But anyway, that's the other thing that will mess up my office hours, because if it does start at 10, that means I will not be here for my office hours. It's normally start at 10. The hearing should be through within an hour. I'm supposed to participate a little bit in the next hearing, and if we can get that done early, but I've got a 12 o'clock class, so I'm going to have to leave there in order to get back from my 12 o'clock class. So those are the only things I know about. I do know that we have class this week, and we have class next week, okay? And I think that gets us into very close to finals week. Let me go back and see if I can find. Oops, I don't have it in this grade book. I thought I'd check and see the previous summer, you know, what days they were, but I believe that's how things are running. All right, any questions on anything we've covered so far? Okay. We're on in chapter 3, differentiation, to me, the core, the main, the absolutely critical part of Cal 1. We're in section 3.9, almost through with this chapter, and we're on example 6, top of page 178. And these are the figures for that. It says differentiate for x is greater than 0. Okay, now we'll talk a little bit about why that's the case. One decided he would show up today. Yeah, that's all right. No problem. Glad you're here. All right. Doubled the class size. Way to go. All right. We're on example 6, page 178. It says differentiate for x greater than 0, and we'll talk about why that's true in just a moment, these functions. All right. Chicken is back. Good. No, you haven't been anywhere, but you couldn't be here. Okay. And here you are right there. Go all the way across the page and stay on the right line to get to you. Example 6, top of page 178. Says differentiate for x greater than 0 these two functions. The first of these is f of x is equal to x to the x. Uh-oh. We talked about before when the exponent was a constant and the base was a variable, that's a polynomial function. And we know how to do those. Or a power function, you could say. But then we talked about what happens if the base is the number and the exponent's a variable. Well, that's an exponential function. Well, what about this one? This is x to the x. Both the base and the exponent are variables. What in the world do we do with that? Anyone got a first idea of a suggestion of what we might try? Trick? Anything?
You just leave that x. Like, multiply by x.
Okay, just a second. Let me get Ricky here, which he is here. Let me mark it here. Okay. Now you say multiply by x, making it x to the x plus 1.
So it'll be 2x to the x power.
Say again?
So then if you multiply by x, it'll be 2x.
Now if you multiply by 2, you get 2x. Okay. If you multiply that expression by x, that would be x to the x times x, just x. That would give you x to the x plus 1. And that's not particularly going to be helpful. I think I thought I was hearing what you were saying was not a bad idea if you pull that exponent down and multiply it. Is that what you're meaning? I thought that might be what it was. You can't do that with a function. You can if you take the log of that function. So that's our first step. Now, it just depends on whether you want to put in another variable. You don't have to, but I sort of like just to make this f of x y. Y is equal to x to the x. And then take the log of both sides. That would be the log of, natural log of y is equal to the natural log of x to the x power. Okay. Now I think you can do what you were suggesting. Okay. That would be x times the log of x. That's what you meant, wasn't it? Yeah, I thought so. Okay. So ln of y is equal to x to the x times the log of x. Now we can differentiate both sides of the equation. And what would that give us? By the way, what we're looking for is, it says differentiate this, so we want df dx. That's what we're looking for, okay? So let's proceed. What happens if you differentiate both sides? Besides Davis coming in, which is a very good thing. Okay. All right. Can we differentiate both sides? Okay, certainly, let's start with the left-hand side, though. What you just said applies to y too, right? What would that be then? 1 over y, but because you're taking it with respect to y, with respect to x, you have a chain rule issue, so that will give you dy dx, okay? because y is a function of x, as you see right here. Okay? Now, I heard what you said at the beginning, that derivative of log x would be 1 over x, and that's absolutely true, but we don't have just the log x. What do we have on the right-hand side? Okay, yeah, it's also a time sign. We have a product rule, don't we? X is a function, log x is a function. It's a product of two functions. Just like will. No, I'm never going to go there. Okay, will is here. Okay. All right. So how do we do derivative of a product? Or can we? You better be able to. Okay.
So it will be zero for x. The derivative of x is 0, right?
Is it? Oh, wow. New calculus. I'm not familiar with this one too much. What is derivative of x with respect to x? 1. Derivative of a constant is 0. Derivative of variable, that would be 1. So I'll understand the 1 there times what? Okay, log x. There's the first term plus x. Second.
Times log of x, log of x is just a number.
Okay, wait. No, log of x is a variable, but the thing is, I understood what you were doing to begin with. Take the derivative of this times that. That's what this one is. Plus, and what's the second part of the product rule? The first times the derivative of log x. And what's the derivative of log x? You told me a minute ago. 1 over x. Okay, listen to her. She knows what she's talking about. Okay, so this is times 1 over x. And guess what that gives you? You know, 1. Exactly. So this is log x plus 1. There's, okay. That's what, okay. Let's write it out what we got. 1 over y is equal to, I'm saying 1 over y dy dx. I can't write. Goodness gracious. Say the right words and write the wrong words. Okay. Okay. Let's try it again. Okay. 1 over y dy dx is equal to log x plus 1. Okay. Now, we're looking for dy dx because f is y, right? These are the same. So what we're going to do is multiply both sides by y, and that gives us df dx. I could have written it anywhere like that, but I just chose to do it here, is equal to y times log x plus 1. Okay? Now, that's what we're looking for, except we want it in terms of x, not y. Well, what was y? What was y? X to the x. So this will be x to the x, and it doesn't matter where you put it, times log x plus 1. There is the derivative of f with respect to x. Do you see that? Now, they probably wrote it in a slightly different way. Yeah, they wrote the 1 plus log x, not log x plus 1. Same difference in front, and then x to x at the end. Fine. Either way you want to write it is perfectly fine. But that just illustrates again the problem with these computerized homework packages that only look for one answer. They would have told you that's the wrong answer where it's perfectly correct. Okay, now, got that one done? And by the way, let's, here is the graph of the function, f of x equal x to x. There, that first graph up there got stuff over. I think I'll erase some of that so you can see it better. Okay. There's the function, and we can find its derivative. Looks like it's a nice, smooth, continuous function, so it should have derivatives. Yes, it does. There it is. Now, where is that derivative equal to 0? Well, we don't even know what x to the 0 to the 0. Well, number one, this is only good for x greater than 0. So we don't care, about x equals 0. The reason for that is, remember what your base has to be when you have a variable exponent? The base has to be some number greater than 0, and also not 1. We haven't put that restriction in here yet, but it's okay. All right, so if this is greater than 0, then this obviously can never be 0, because anything greater than 0 raised to a power greater than 0 is not going to be 0. So it's where this is equal to 0. Well, where is that equal to 0? Where log x is equal to minus 1. Log x is never equal to minus 1. So we do have a problem here, don't we? But they didn't ask for this, so we won't go into that. You'd have to do a little bit of numerical work on that to find out where that derivative is 0. Obviously, it does have 1, but it's not not going to be an easy one to find. And they didn't ask us for it, so we're not going to do it. Let's go to the B part. I hate to erase all this, but I don't have enough room to do the B part. Here's the B part. And again, we're doing x's greater than 0, okay, for the reasons we already talked about. And we're taking they're asking us to differentiate this. G of x is equal to x to the sine x. How would you approach that problem? What would be your first step? Would you have a first step? Please take your first step. We'll all cheer. What would be your first step? Take the log of both sides. Now, do you mind keeping it in G, or would you rather change that to a variable Y? It doesn't matter to me. G's fine, okay? So this will then be the log of G of x, okay, is equal to the log of x to the sine x, okay? Can we rewrite that second one? Please say yes. All right, how? Sine x times the log of x. Very good. The exponent moved down. Rule of logarithms. Okay, now what do we do? One of those questions. Take a derivative. And what's the derivative of the left-hand side? 1. How do we get that? Another new calculus feature. What's the derivative of log? One over, okay, but it's 1 over g of x, okay? But we have another part to it. Chain rule. Say again? Not g of x, g prime of x, or d dx. So let's just do it g prime of x. It's easier to write. Okay? This is equal to, now we go to this one down here. We sort of ignore this one. We already cleared that. What would that give us? Okay, you're taking derivative of the first, that would be cosine x times log x plus sine x times over x. Yeah, very good. Excellent. Okay. Now, really don't like to see that. It's going to be messy either way. But anyway, now all we've got to do is multiply both sides by g of x. So this gives you g prime of x, which is exactly what we're looking for, is equal to, and since they wrote it the other way before, let's assume they're going to write it that way this time. So let me, okay, right. I think this is just messy, but cosine x times the log of x, okay? Those are two different functions. I don't know if you put them in parentheses or what, to make sure you don't think it's cosine of x log x. It's cosine of x times the log of x, okay? Plus sine x over x, okay? And then we multiply that by g of x. But what is g of x? X to the sine of x. Okay, that's it. I mean, it looks really complicated, but when you get around to doing it, it's not that bad. Now, they wrote the sine x over x first, it doesn't matter, plus cosine x log x, and they put the cosine x in parentheses, not log x, it doesn't matter. All that in parentheses times x sine x. Very good. A pretty messy looking function, but it still has the derivative. And again, and I'm sort of jumping ahead here, where is that equal to 0? Well, x to the sine x is never equal to 0. So we're forgetting about that. So it would only be where this was, and that's where this thing is equal to the minus of that thing is. So glad we don't have to solve that. But you see it does have a horizontal derivative here, there, 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 and then looks like maybe another one there before it goes up again. We're not doing that yet, thank goodness. Okay. Almost have to have that done, what do they call it? Numerically rather than analytically, because analytically that would be a pain in the neck to try to figure. All right, now the next issue in this section is hyperbolic functions. Now, have any of you ever run into any hyperbolic functions? I've asked students in just about every time I get here, and they say, no, we didn't cover that. And if students who I had Cal 1 at another school, they said, no, we didn't do those. Calculus books love hyperbolic functions. To me, let me explain what a hyperbolic function is. It's basically a made-up name, okay? There's nothing necessarily hyperbolic about it, and there's nothing that's really very triggish about it. But here's how they define what a hyperbolic sine is. And that stands for hyperbolic sine. And that's defined as, is defined as e to the x minus e to the minus x over 2. Okay? And hyperbolic cosine of x is defined to be e to the x plus e to the minus x over 2. So the first is the difference, and the second is the sum. That's it. Now, then they go into doing derivatives of it, which are fine. Except the thing is, those are exponential functions. To me, it's just as easy to take derivative of exponential. They're really easy to do. And you sure enough wind up with this thing here. So why introduce a new function when they're so easy to work with just as exponentials? But I want to point out to you, they look a little similar to the trig functions. They're not at all related to trig functions. But that the derivative of the sine is cosine in trig derivative of hyperbolic sine is hyperbolic cosine in this. So that would be one advantage. But then when you get to hyperbolic cosine, its derivative is not negative hyperbolic sine, hyperbolic sine. So to introduce this just because there's a few similarities, but not all similarities, so then you have to keep up with the signs. Basically, I look them up anytime I ever need to do it. So why do it? I can take the derivatives of those things and find out with no problem and still have it in a form that's a lot easier to use than the hyperbolics. But mathematicians, I guess for a long time, loved them. I'm not going to require you to do any because I've never, so far, found anyone who says, oh yeah, we use these all the time. I found nobody that uses them. So next is the derivatives of hyperbolic and trigonometric functions. Again, they're showing you these. Like I just showed you those. I didn't blow it up. I probably should have. Make it easier for you to see. Okay? And again, you're not responsible for this. The derivative of tangent is secant squared. The hyperbolic tangent is hyperbolic secant squared. You might ask, what in the world is hyperbolic secant squared? Well, that's just 1 over hyperbolic cosine squared. This is sine, hyperbolic sine over hyperbolic cosine. But they're just exponential functions. Why mess around with all these new names? Then when you get to this one, it's a minus, and that was a minus. So yeah, everything's looking pretty good here. Until you get down here, this was secant tangent. This was minus secant, minus hyperbolic secant minus hyperbolic tangent. And then this one is very much the same. So you see 3 out of the 4 are very similar, but not quite. That fourth one. And which one is it? It's that one is the one that's different. And why just have another set of things? And I can see why you do sines, cosines, tangents, and things. Those are trig functions that make sense. Hyperbolic, they're exponential functions. Why not just use the exponential? So again, you're not responsible for this, but in case you ever need it, here they are. I'd say look them up, because I don't expect you to memorize. I never bother memorizing. Okay? Now, and by the way, your marginal note shows how they define hyperbolic tangents and secants and cotangents and cosecants, and it's just like you would expect. It's just the hyperbolic sine over hyperbolic cosine. Yeah, they're all exponential functions. Okay, there. Yeah. Now, sure, when you get into hyperbolic tangents, hyperbolic cotangents, yeah, those do get a little messy, but guess what? I haven't found anyone who's ever used them, so why? Okay, so never mind. All right, enough about this. And then they show some of the identities, and back from chapter 1, if you want to go back and review those, you can. I don't use them, so I don't know of many people who do. Okay, example 8, I think, is dealing with this, but it's pretty reasonable. I want to just show you what a hyperbolic cosine function looks like. Okay? It's this. It's not a periodic function like a cosine function. It's just the red function. It just goes on. It's an exponential function, only it's the sum of 2 exponential functions, half of the sum, and it goes like this. Then when you're talking about inverse hyperbolic cosines, you've got something like this. Well, what does that look like? That looks a whole lot like a log function. Okay, and it really is a lot like a log function. It just doesn't extend down here. Because if this is related to exponentials, this is related to logs. Okay? Here's your hyperbolic secant function. Again, not a periodic function. It doesn't repeat itself. It doesn't have vertical asymptotes like secants do, or tangents do, or cosecants or cotangents. It's just a function. It's an exponential function. Okay? It's basically the inverse of this one. 1 is 1, and where this is going up, this is going to 0, and this 0. And these are the actual hyperbolic, but the only part that has an inverse is the part that's 1 to 1. So this is what these are the inverse. So if I've never used a hyperbolic secant, why would I ever use a inverse hyperbolic secant? I really don't know the fascination with it, but I'm sorry, I should have blown that up. But it seems like calculus books love them. You know, they always have sections of them, but then I still don't think I've ever seen anyone who used them. And I may be wrong. Maybe some field uses them all the time. I don't know. Check with your people in your major and see if you ever use them. If you do, you might want to pay more attention to them than I'm giving you opportunity for here. But I'm not going to require homework on them or anything else. You won't be asked any of these on the test. If you do run into them, you've seen them, you can look them up in a table. So here's the inverse hyperbolic functions. Domain for inverse hyperbolic sine. They didn't show you that one. That one has all x. Look at the domains for these. Bizarre. Greater than or equal to 1. Absolute value less than 1. Absolute value greater than 1. 0 to 1. And not 0. So really, just remembering where they're defined is more than I ever wanted to do. So if you ever need them, there they are. I would say if you ever need them, you probably would be better off just dealing with the exponential functions and doing whatever is required there. Okay, you've seen them. That's all that I'm going to say on them. Okay. There's a little bit of me that wants to compare them to inverse sines and cosines. There's just not enough similarity to make them even worthwhile doing. Okay, so I'm not. Okay. This, I think, is part of example 9, and since it deals with hyperbolic, not even going to mess with it. All right, any questions on 3.9? If any of you need to or want to know hyperbolics, I'll go over them. But otherwise, that's all I'm going to do. Any of you feel an urgent itch to deal with hyperbolics? How about the preliminary exercises? Anyone interested in those? I'll be glad to go over those if those help you see the concepts better. What you think? Yay or nay? I heard a nay. Okay. So your homework exercises here are any of the odds 1 through 19. There's a pretty big passel of those. Any of the odds are either 21 or 23. Any of the odds 25 to 35. Any of the odds 37 to 43. Any of the odds 45 to 49. And from that point on, I think they're all hyperbolics, so you don't have to do any of the rest of those. Let's see if, well, until you get to more of the word type problems. Any of the odds 79 to 83. Okay? Now, especially looking at those, there's a couple things you might see. One is the Richter scale is mentioned. Energy radiative seismic waves from an earthquake measured on the Richter scale. So since that has to do with, and this question particularly to do with calculus, you can write on that if you find that an interesting enough topic. Number 81 deals with the logistic equation. And I wish they had shown the graph of that, but that's one used a lot. It's used in all sorts of areas. Population growth, that type of thing, you know, whether you're talking about human population or animal population, I would guess also decline of populations, bacterial population growth, you know, all sorts of things there. It's also used a lot in disease. My wife's an epidemiologist at UAB, and she uses logistic. I'm not sure she knows she's using logistic equations all the time, but the statistics they do are logistic, based on this logistic equation. And if you see the first three letters there, logs, they play a big part of this. Okay, so if you want to write on logistic equations, there it is. Now, by the way, I keep mentioning these papers. This class, let's see, 3 out of 12, 1/4 of the class is turned into paper, and we've only got 2 more weeks of class. So please, folks, take advantage of some of these weekends and get your papers done. Unless you work better in the week, you can do it during the week too. Number 82 is referring to the Poisson-Boltzmann equation, electrostatic forces in certain molecules. So that's a lot more physics, but Poisson is very much a mathematician, and there is one that has a hyperbolic tangent in it. I have a feeling that could have been done just as nicely with exponential functions, but what's for me to say. So there is an example of one you might use, but if you don't want to get into that part, and who is Poisson, what are some of the other things he did, Boltzmann is much more of a physicist than a mathematician, but you could write on him as well. He shows up here. The Palermo Technical Impact Hazard Scale, quantifying the risk associated with the impact of an asteroid colliding with Earth. If some of you are into that, there's a thing you could proceed. Then further insights and challenges. There aren't but a couple there. I don't see anything there that I would pay too much, well, pay as much attention if you want to it, but you're not going to be quizzed on that. Okay, related rates. I wish we had time to do these. These are such fun problems to do, but we just don't have much time left in the term, so we're going to have to skip that one. Okay, and that ends it for chapter 3. Now, I think I gave y'all, those who were here, the test for chapter 3 last time. Is anyone here today who was not here last time that needs a copy of that test? Okay, let's see if I can find those. Test 1. By the way, if you haven't turned in the first test, I need those in, because I'm giving you the second test now, if I can find it. I think I've gone too far. Okay, go back. Test 1, test 1. Still test 1. Here's test 2, but that's... Oh yeah, that's it. Okay, I'm sorry. Right past it. Anyone else need test 2? Those who have test 2, let me just make sure. First question, what is the derivative of the function x to the 4th minus 2x plus 7? Is that the test I gave you? I have several versions. I want to make sure I give everybody the same one. Anyone has it? Huh? Where you were working on it, so like, yeah, I remember. Okay, I got it. Okay. All right. Is that how it begins? Okay, that's the right one. All right, good deal. Everybody else got a copy. Kenny, you go. I gave you one earlier. Okay. Losing that. All right. Well, let's move on then to. And by the way, I didn't mention this. If you want to look at some of the review exercises, if the homework exercises haven't been adequate for you and you want a few more to look at, any of the odds of those answers are in the back too. 1 or 3, any of the 5 or 7, 9 or 11, or 13 or 15, any of the odds 17 through 23, do 25 if you need to review that, 27, any of the odds 29 to 79, we'll pass a lot of them. Well, I wouldn't say 79, I'd say through 75, okay? And then 83, any of the odds 85 to 89, and any of the odds or either 91 or 93, 95 through 99, 101 to 105, 107, any of the odds 109 to 113, either 115 or 117, 119, any of the odds 119 to 120. Well, those get into related rates, so you don't have to worry with those. All right, done. I think that's the last slide here. So what we're going to do is move to chapter 4. And I'm trying to remember now what in the world is section 10. This is just trying to remind myself. This may be related rates, which is fine. We skip that section. I'm just seeing what it is. No, that was, I think we already did this. That was implicit differentiation. Okay. And I think the next section was related rates. Okay. Knew we didn't skip 2. Okay, get back one more. Go to chapter 4. Take a while to open. All right, now the figure you see here is not the same one you see in your text, unless you have an old text. But this is functions are one of our, blow this up a little bit. In case you had not realized how important functions are, here you might say, well, what do we ever use? In fact, I hear the question all the time. What are we ever going to use this for? Functions are one of my most important tools for analyzing phenomena. Biologists have studied the antler weight of male red deer as a function of age, okay? That way, when they find a deer, or someone's killed a deer and weigh the antlers, they can estimate their age. You might say, that doesn't sound very important, but when they're studying population growth and where they're, you know, they need to, if something interfering with the development or knocking them off early, need to know that. In our book, they show sun tracking mirrors known as heliostats in the Tabernas Desert in Spain. Use the principle of least distance, which is a function to construct the sun's light and generate energy. Those are the most efficient kind of solar patterns. They follow the sun. A lot of the ones you see, the panels that are on roofs and stuff, they're fixed. They're hit to get the maximum intensity during the maximum part of the day, but then they can't move. These are even better. But you see all sorts of applications for functions. Now, first thing they do here, and to me they spend way more time than they need on this, but it is important. Linear approximation and applications of that, okay? In some situations, we're interested in determining the effect of a small amount of change. That's what a derivative is all about, right? Giving you small change of x with change of y, change of y with respect to change of x is that change of x goes to 0. So what if you have a very small change? What can you estimate, okay? How does a small change in angle affect the distance of a basketball shot? Well, it could have a pretty big difference. How is the revenue in the box office affected by a small change in ticket prices or apartment prices and stuff? The cube root of 27 is 3. How much larger is the cube root of 27.2? Okay? These are all cases in which you're doing just a little bit of change and wondering how that's going to affect an outcome. Okay? And here is basically, seems like we're going backwards now. Okay? We found out what derivatives are, and now we're going to go back to deltas, not d's. Okay? Now, you didn't notice this, okay, your change of f is the f value at a plus a small additional x minus the f value at a, okay? So this is your delta f way back that we did at the beginning. Maybe early on we called it delta y. This is going way back, okay? You almost did the same thing when you did slopes long before you knew what calculus was, okay? And where the delta x is pretty small, that measures exactly the, not exactly, but it's a good approximation of what your change of f is. Well, I mean, that is your change of f. What it was at a little bit further down the road from what it was previously, f of a, that's your delta f right there. That is an equal sign. Now, where that delta x is small, then that leads to a linear approximation. And to keep from beating this into the ground, here's what that linear approximation is. Now, our book has a little bit bigger definition than this one. I think this one splits it into two. I'll take a look in a minute, but here's the first. The linear approximation of that delta f, okay? You know the delta f is a change of what it was f of a to what it is when it's f of a plus a little bit, okay? If f of x is differentiable at a, and that delta x is small, then your delta f is approximately equal to f prime of a, which is something easy for us to calculate, times that delta x. In other words, what the function, okay, the change of this delta f, the f, is that derivative times that change of delta x, okay, change of x. And if you think about this, if you divide both sides by delta x, you almost have df dx is equal to df dx, right? So yeah, that makes perfect sense. Where the delta f, of course, is the f at the new delta x, a plus delta x minus f of a. So this, the left-hand side here is this thing right here. That's the approximation. And that's the part that our book did an additional line on to say that. So I'm going to write it down for you since they didn't in the slide set. And I can't write it here until I shrink this, okay. And I think I need to get my pen reactivated to dark. Okay, so then this leads to f of a plus delta x minus f of a. How much is f changing? That's approximately equal to f prime of a times delta x. Now, I said it looks like we're going backward. Guess what? I don't think I want to calculate the function twice here and take a difference, when all I have to do is take the derivative, which is a pretty easy thing, and multiply by that difference. This is the easier step than that. It's not going to give you exactly, but it's going to give you a pretty good approximation. Okay? Now, what you're really interested in is this. Okay? What this gives you is a good approximation of that. The linear approximation is sometimes called the tangent line approximation, and I think this next figure illustrates that. Okay, blow this up a little bit. Okay, here's your curve, the blue curve. That is your f of x. Okay, here is your alpha a. There's a. And this has a big delta x here. There's your delta x over there. A plus delta x here. So f of a plus delta x is this value. Now, what is the linear approximation? That this delta f is approximately equal to the derivative of f, that's the tangent line, at a times the delta x. Okay? So that says it's a linear approximation. You're saying here's what the derivative is here. There's your delta x. There would be approximately your delta y. It's not exact. There's really your delta y. This is not a bad approximation. Not great, because that delta x is way out there from where A was. If you had pretty small delta x's, though, say in that range, that's a really good approximation, right? Because those lines are almost on top of each other from here to there, okay? So that would be an even better approximation of your delta f. This delta x is a really large delta x, and it's still not a bad approximation, okay? So I would say that is not for a small delta x. For small delta x's, it gives you a really, really good approximation, okay? I think they don't have a graph for example 1, so let's do it. Use the linear approximation to estimate 1 over 10.2 minus 1 over 10. Okay? We're going to use the linear approximation to estimate that. Okay? It looks like to me, because this is right on the crease of my book, they say, and hence 1 over 10 minus 10.2 dot. And I don't see what's supposed to follow the dot. But anyway, let's just do that. Okay. Well, first, using the linear approximation, what would you say your function was here? What's your f of x in this case? What would be your guess? What's your f of x here? Say again? No, okay, that's a value. The f of x would that be 1 over x? Okay? And then we're going to let x equal 10 and then 10.2, right? Well, if that's your function, what's your derivative? F prime of x. We can do that, can't we? Another way to write 1 over x, I don't like to write in quotient form. I would prefer to write in exponential form. How would you write 1 over x in exponential form? X to the minus 1. Now that I found a lot easier to differentiate. So what's f prime now? What would that be? Take the derivative of f in that form. Negative x to the negative 2. Now rewrite that in quotient form, and that would be minus 1 over x squared, right? So there's your derivative. Well, what we're interested in is what is that when x is equal to 10. So f prime of 10 would be what? Negative help me, it's not that hard. Anyone got it? No, it's a 10. 10. It's like all those are 10s. Yeah. It's negative 1 over 100. And if you wrote that in decimal form, it'd be negative 0.01. Okay. Feel like a dentist here. Okay. Now, what does your linear approximation tell you? The delta F is approximately equal to F prime of A times your delta X. Okay, what's your delta X here? How much is X changing? 10 is changing from 10 to 10.2. So what's your delta X? Your X was 10. You're wanting the difference then, 1 over 10, which is 1 over X, plus delta X minus 1 over X. What's your delta X? All these hints are getting bothersome. What's your delta X? No, it's 0.2. Your X was 10, okay, right? Your delta X then would be 0.2, because X plus delta X, okay? So the delta X is, in this case, 0.2. Well, your F prime of X was minus 0.01 times 0.2, and what would that be? Negative 0.002. Okay, that's your approximate difference between those two values. Let's actually do them, okay? They're easy enough to do. Do 1 over 10.2. You got a calculator? You could do a 10.2 to the minus 1 if you want to do it that way, however you do it. Minus 1 over 10, or 0.1. What you get the difference to be? Okay, say that again. I'd say our approximation is pretty good, wouldn't you? This was negative 0.002. That's negative 0.00198. Awfully close to 0.2. We're off by 2 10,000ths, okay? I can live with that, I think, okay? Now, so you see, this is our linear approximation. The change of F would be your derivative times the change of X. It's pretty easy to calculate. Your actual values, you have to use a calculator to actually do that. These, I think we did everything in our head. We didn't even need a calculator, I hope. Okay? All right. And then they say, what's the error? It was negative 10 to, less than 10 to the minus 4th. It was actually 2 times 10 to the minus 5th. Yeah. How did I get 0.2? That was your delta X. Okay. This was telling you X is equal to 10, right? Okay? Well, your delta X, as you're going from 10 to 10.2, your delta X is 0.2. Right? How much the X has changed between here and here is 0.2. That's your delta X. Make sense? Okay. Now. Okay. Now. They do a little blurb on differential notation as if it's a lot different. It really isn't, okay? Let's blow it up here. Just can't believe they put that on a slide and make it that small. Okay. All right. Now, this is exact here. dy is equal to f prime evaluated at a dx. This isn't an approximation now. This is exact. And what this is just dy dx is equal to f prime. dy dx evaluated at a would be f prime evaluated at a. You just written that in differential form rather than derivative form. So that is an exact value there. Now, what you get to is then say your delta y is approximately equal to that, except now it becomes a delta x. Okay? So, example 2 is using differential notation, they say. I don't think there's a thing for it. There is not. Oh, no, here's the second thing, the one we just did, that your delta y is approximately equal to dy. From our last equation to this one, it's just as another way of getting to the same thing we've been dealing with. All right, so let's get out of that and do example 2. They don't have a figure for example 2. How much larger is the cube root of 8.1 than the cube root of 8? Okay? Well, you know what the cube root of 8 is, don't you? 2. Okay. How much larger is the cube root of 8.1? Okay? What do you reckon we would do for that? Say again? Okay. Okay. What function are we dealing with here? What are you doing in both of those? Taking a cube root, yeah. So our function that we're interested in is f of x is equal to, I like to write it as x to the 1/3, right? Okay? And guess what we'll do next? One of those questions. Take a derivative. L prime of x is equal to 1/3 x to the negative 2/3. Yeah, you're subtracting 1 from 1/3. So you're subtracting 3/3 from 1/3, which would be negative 2/3. Okay? Now, if you then were to write as we did before, dy is equal to f prime dx, right? That is exact, right? That's what we did before. That one right there. dy is equal to f prime of a dx. Okay? So here all we need is figure out what a is. What is you think your x is here? What is the a value in this problem? Okay, actually the x would be 8. Okay, the delta x is 0.1. So you're getting there. The delta y is approximately equal to this evaluated at x equal 8. Okay, well let's evaluate that. F prime at 8. Well, that would be 1 over 3 times the cube root of 8 squared. That's what 2/3 is. I wrote it in the denominator. You can't see my cube there very well. Let me see if I can clean that up a little bit. Probably going to erase everything, but okay, it did, which is fine. The cube root of, that's still not very pretty. The cube root of 8 squared. Okay? What's the cube root of 8? Squared is 4 times 3 is 12. So this is equal to 1 over 12. There's the f prime at 8. So that would be 1/12. And your dx, what did you say it was? 0.1. Got it. So if you'll do 1/12 times 0.1, what do you get? 0, 0, wait, 2 zeros? Yeah. I thought you said 2, but I only wrote 1. Okay. 0, 0, 8, 3, 3, 3, 3, 3. I'm just going to put a bar over it. Okay? So for all practical purposes, it's less than 0.001. In other words, less than 10 to the minus 7. Okay? So, pretty good approximation. Okay. Now, someone get your calculator and do the cube root of 8.1. Say that again. Wait, the cube root of 8.1? I think you did. Say again. 2.0083. Okay. Look at what we got. And the difference of that and 2, I mean 2 minus that, would be 0.0083. Yeah, I mean, you're right on the money. Okay, very good. All right. Now, anyone ever seen anything that looks like this? Okay. When engineers need to monitor a change in position of an object with great accuracy, they may use a cable position transducer. That device detects and records the movement of the metal cable attached to an object. Its accuracy is affected by changes in temperature because the heat causes the cable to stretch. The linear approximation can be used to estimate those effects. And that's a cable position transducer. One application of transducer was used to compare the changes in throttle position on a Formula One race car with the shifting actions of the driver. All right, fine. The best I can figure, the cable actually goes through there, and this is measuring how much the cable is shifting. Okay, that's my interpretation of it. It's the only thing I can figure. When I first looked at this, I thought that was a speed gun that they're measuring the speed of baseball, say how fast is the pitcher pitching, or if y'all watch Wimbledon, how fast is the server serving, you know, and those kind of things. But this isn't quite the same thing, but it does look a lot like it. When I first looked, I thought it was. So anyway, they say that if you go up in temperature, you have to adjust your calibration because the cable increases slightly. Okay, so the next example is thermal expansion. A thin metal cable has a length of L is equal to 12 centimeters. Okay, when the temperature, and by the way, capital T usually stands for temperature, is equal to 21 degrees Celsius. Approximately what is 21 degrees Celsius? Anyone know? Yeah, I bet you grew up with them, didn't you? Or not? No, you didn't. Okay, I bet your parents did. Most of the rest of the world, except us, use Celsius. We're the only country, industrialized country in the world that still uses Fahrenheit. Okay, so I'll just give you a clue. 20 degrees Celsius is right near room temperature. So this is right at it. 20 degrees Celsius is 68 Fahrenheit. I bet you this is very close to what our room temperature is right now, What does that say? 71? Second? 71. That is so close to what our room temperature is. So think of that as room temperature. Okay? So that has the length at room temperature. Estimate the change of length when T rises to 24 degrees Celsius. So what we have here, this is your T1. You got T2 going. Goodness gracious. T2 is going to be 24 degrees Celsius. You anticipate very much of a change? I sure don't. Okay. Here's what our assumption is. dL dt, and this is, by the way, the law of thermal expansion, is equal to K times L. Okay? And K is the coefficient of linear expansion. There it is. I was trying to find it. I knew they had it written here. Where K is 1.7 times 10 to the negative 5, and it's per degree Celsius. That's how much the length changes per degree Celsius. Okay? Coefficient of thermal expansion. Okay? Often called linear expansion. Okay? Okay. Now, this already tells you the derivative. Okay? So what we want to know is, for a, what else do we need to know here? Say it. I can't hear. Change of what? You may be saying it right. I just don't hear well.
I said the change of heat from T1 to T2.
Okay, that's your delta T as temperature, not heat. But okay, the delta T here is what? 3 degrees Celsius. Okay, got it. Okay, well, what's the question asking for? Estimate the change in length. Well, that's going to be your delta L. That's what we're looking for. And what did our equation tell us? Delta L is approximately equal to dL dt times delta T. Right? Okay. Now, our original length was 12. So what we're going to do here, the dL dt is this, and that would be 1.7 times 10 to the minus 5 per degree Celsius, and multiply that by the length, and the L was 12 centimeters. Okay? So that gives you, you can punch it in your calculator and see, that's what this thing right here would be. So delta L, which is what we're looking for, is approximately equal to, what is that? 1.7 times 10 to the minus 5 times 12. .7 times 10 to the minus 5 times 12. It takes a while, huh? Say again? 3 zeros? Is it? And what? 204? Okay. Sorry, my hearing is so bad. Okay. Take this and multiply it by your delta T, which is 3. And by the way, this has units, so let me take care of the units too. What are those units? They are centimeters per degree Celsius. Centimeter per degree Celsius. Okay? Okay? Multiply that by 3 degrees Celsius, and that's your change of temperature. So multiply that by 3, and what you have is approximately 0.000612 centimeters, because degrees Celsius cancels out. So that's what your change is. About 6.12 times 10 to the minus 4. Not going to be a lot, is it? Okay. They rounded it just to be 6 times 10 to the minus 4 centimeters. Does that make sense? Okay. Good deal. All right. Yeah, I think the next one does have a slide too. Let's look at this first, and then we'll shrink it back and actually do it. Okay. The effect of an inexact measurement. The Cheesy Pizza Parlor, there's several things cheesy could stand for there, claims that its pizzas are circular with diameter of 50 centimeters, as shown in this figure here. Okay? What is the area of that pizza? If its diameter is 50 centimeters. How do we get the area? Anyone know the formula? Supposedly it's a circular pizza. Okay, pi r squared. I always thought power around, but you said pi r squared. Okay? Never mind. Okay? Now, can we use that here? How? Aha! Because that was diameter, not this. So that's 25 centimeters squared. Okay? 25 squared, I think, is pretty close to 625, isn't it? 25 squared. Oh, good. Okay. All right. All right. Close to it anyway. So that would be 625 times pi, and that would be square centimeters. Pi is about 3, so okay. So there's your square centimeters. Okay. All right. So the first part was just a little bit of geometry. Okay. What is the area of the pizza? Now, the big question is, estimate the quantity of pizza lost or gained if the diameter is off by at most 1.2 centimeters. Okay? So when I see that, I immediately say delta, and it says diameter, delta D, like the old song Delta Dawn, but not something very different, is equal to 1.2 centimeters. Okay? That's your change of diameter. Okay? And it says estimate the quantity of pizza lost or gained if the diameter is off by at most 1.2 centimeters. So, what are we going to, what's our function here, you reckon? And by the way, I want to go on and change that to delta R is equal to what? Delta D was 1.2 centimeters. Delta R would be, help me. How's radius compared to diameter? You did it just a few seconds ago. Minutes now. Yeah, 0.6 centimeters. I like to use that rather than diameter. Okay? The picture shows diameter, so I'm more interested. but you know, if they advertise in terms of diameter, then they need to stick with it. But to do the problem, I like to deal with gradients. So, what are you looking for? It says estimate the quantity of pizza lost or gained if the diameter. And what is your quantity of pizza? What are we using here? Area. So what we're looking for, the change of area. So delta A, how is it related to a delta R? Can't you almost imagine how to fill in this? Isn't that what you would need? If you had, this is the R here, that's an R. Delta A would be approximately dAdr times delta R, right? That's our linear approximation. I mean, that's divided by delta R, you get delta over delta R is approximately dAdr, right? That's what those deltas stand for, infinitesimally small. So there's your differential form. So guess what we're going to have to do? Take the derivative of A with respect to R. And what would that be? dA is approximately, well, is exactly okay, you have coefficient of 2, right? Pi is just a number, so it's 2 pi r to the first power, right? So there's your derivative. So now your change of area is approximately equal to 2 pi, and your original radius was 25 centimeters, okay? Then you're going to multiply that by your change of r, and that was going to be 0.6 centimeters, right? So this will be, and that's going to be plus or minus whether it's bigger or smaller. So this will be 50 pi centimeters times 0.6 centimeters. I think I can almost do that in my head. Isn't that 15? Not sure I can do it in my head. Let me. 30. Yeah, there's 3. Yeah, sorry. I think that looked at all right. Okay, that would be 30 pi centimeters squared. So there's your delta R, delta A, either plus or minus that amount. Okay. Multiply that out, that's about 90 square centimeters approximately. Okay. Now they use D, I don't know why. Let's see what their final answer was. Plus or minus 94.2 square centimeters. I just estimated 90, so that's pretty good. If you want to get it exact, 30 times pi, do that on your calculator and see what you get. Okay, maybe you don't get it. 94.24, is that what you said? Yeah, they rounded to 94.2. Okay, now, how much did that change? Well, what's the percentage change? This is the amount of change. Out of that, basically, why mess with the decimal forms? That would be the percent difference would be approximately 30 pi over 625 pi. The pi's go out. Pizza pies? Never mind. Okay. And this would be 5 will go into that. 6 times 5 will go into that. 125, I think it is. Yeah. So 6 divided by 125. What is that? Anyone got it? 6 divided by 125. Say again? 0.048. Okay. And let's see what they got. Yep, well, that is the decimal. If you wrote that in percent, that would be about a 4.8% difference in pizza. Plus or minus. Okay. Make sense? If I want it, I want to make it bigger, okay? Okay. I love pizza. Okay. Now, this looks like something we just had, isn't it? The approximate, let's see. Does anyone need, I wish I'd have caught it when you left. Anyone need to take a quick bladder break? I wish I had seen you when you walked out. I must have been looking at the board. Want to take a quick, just a stretch break or anything? Huh? Not really? Okay. Some point I may have to, but if so, I'll say, we are going to take one. Okay, I won't ask you, but since you had taken one, I thought others might need it as well. Okay. Now this is very similar to what we were just doing before, so it seems like it's almost a bit redundant here, but it's okay. To approximate a function f itself rather than the change of f, we use the linearization L of f centered at x equal a and defined by okay. And I mean, for the life of me, I don't see why they write it two different ways. But anyway, let's just take it. Now this looks very similar to what we were doing before, but now we're actually doing the approximation of the function rather than the approximation of the difference, the delta, the change of the function. Okay? The tangent line is a good approximation in a small neighborhood of the point P, where P is a f of a. Okay? A on x, f of a on y, so that's your point P. Now, it would have been even better to circle that radius, okay? It's still not bad out to there. It's just a little bit of difference here and here on the very outer regions, but the closer you get to P, the better that approximation is. Tangent line is a good approximation in a small neighborhood of P, where P being the point A, f of a, okay? We're not talking about delta f now, we're actually talking about f. What's your linear approximation there? Okay. Here is that linear approximation. Okay. Approximating f of x by its linearization. If f is differentiable at some point a, and x is close to a, then f of x, being x some value close to a, is approximately equal to its linear approximation, which would be linear. What pops into your mind when you hear linear? Say again? Slope. There's your slope right there, f prime of a. Okay? And this is almost your point slope formula. If you say f of x minus f of a is equal to m times x minus a, there you have it exactly. But since we're not interested in the difference, we add the f of a to that side. That gives you your linear approximation. Okay? It's not exact, but it's pretty close. Okay? Your exact value would be whatever that function is. The linear approximation would then be this. The slope, L prime of A times x minus A plus the original value at A. Okay? Now, okay. All right. I just asked, but now I think I will. I guess psychologically I got to thinking about it, so now I'm going to take a quick bladder break. All right, where we left off, they have a little conceptual insight here, which may be helpful to you. Somehow to me it's almost as confusing as it's helpful, but it says, keep in mind that the linearization and the linear approximation are two ways of saying the same things. Indeed, when we apply the linearization with x equal a plus delta x and rearrange, we get the linear approximation. So you can see them play around with that, and it gives you, like they say, the same thing. But here's example 5 then. Okay? Compute the linearization of f of x, and it's written here, well, here it is right here, so I won't write it again. Where f of x is equal to the square root of x times x to the e to the x minus 1 at x equal a. Okay? So, what you reckon the first thing we're going to do to that is? It's one of those questions. Take a derivative, why not? Okay? Now, you don't have to do that first, but why not? Remember, let's just go back and remind ourselves, because it was a couple minutes ago, the linearization, that's what they're asking for, is this thing right here. The f of x, the L of x is f prime of a times x minus a plus f of a. So there's several things you got to do. And which one did you want to do first? You got to do them both anyway, it doesn't matter. Say again? Okay, you want to do the derivative, is that what you said, or do you want to actually calculate it? I couldn't hear. You got to do both of them. Okay, well tell me which one you're going to do first. Okay, but what do you want me to do to it? Evaluate it or take a derivative of it? Okay, let's take the derivative. Okay, f prime of x is then equal to okay, I did the easy part, you do the hard part. Okay, so you want, okay, I'm sort of hearing that you may want to rewrite it first. F of x is equal to x to the 1/2 e to the x minus 1. Is that what you're saying? Okay, yeah. Now let's take the derivative of that. (1/2) x to the negative 1/2 times e to the x minus 1. Is that what I heard? I thought I did, okay. Next. Are we through? Plus, okay, I like that. X to the 1/2 e to the x minus 1. Done. Okay, that part was pretty easy. Now, two other things we got to do, and they're somewhat similar, but a little different. We got our f now of x, and we got our f prime of x. I'm going to rewrite the f prime a little bit, maybe just to help a little bit. That's the same as e to the x minus 1 over 2 times the square root of x. Is that all right? And this will be plus the square root of x e to the x minus 1. Just to get it back to radicals, they're a little easier maybe to calculate. Okay? Now, one of the reasons I want to do that, remember what we got to have to do? We need to do f at a, in other words, f at 1, and we need to do f prime at 1. That's why we're looking at that. Okay? So let's, all right. Maybe it was helpful to write down what we're looking for. L of x is equal to, and I'll write it the way they did, they rearranged it a little bit, f of a plus f prime of a times x minus a. That's the thing we did before. So what have we got to do? Evaluate. Yeah, plug it in. So let's plug in and see what f of a is. F of a would equal, what is our a in this problem? 1. Okay, so we do f of 1. Okay. And that's one of the easier ones to plug in. So what would that give us? Second? Okay. Okay, is square root of 1, which is 1, e to the 1 minus 1, which is, yeah, e to the 0, and e to the 0 is 1. So that's 1. Okay, got it. So this part is 1. Okay. Now we got to do the other part, f prime at 1, and that's why I wrote it this way. What would that be?
0.
How do you get that? Second? Okay, what constant are you looking at? Not that. Okay, not 1. Plug it in here. Plug your f prime. This is f prime of x. Now do f prime of 1. Not of what you evaluated, but this. That's why we did this. What does that give you? 1 over 2 plus 1, which would be 3/2 or 1.5, however you want to write it. Okay? Okay? I think I'd just as soon write 1.5 up here times x minus 1. Okay? So this would be 1 plus 1.5x minus 1.5, right? Which would be 1.5x minus 0.5. Okay? No, yeah. It's pretty ugly. Let me clean that up a little bit. Okay? That's the linear approximation there. Well, let's take a look and see how that looks. Well, this says that you have a slope of 3, or they use 3/2, I have changed it, 3/2, minus 1/2. Yeah, it looks like the y-intercept would be pretty close to that. So yeah, there's your linear approximation for this function near x equal 1. And on this scale, that looks pretty good within that. Okay? Pretty good. Now, if you went up to 0.5, 1.5, that's a huge x. Terrible approximation there. But if you're in this range, very good approximation. Okay? They did 3/2 x minus 1/2. Same thing. Okay. The linearization can be used to approximate function values. The following table compares the values of the linearization to the values obtained from calculating for the function f of x, that very same function. So this is the table that lists those. Goodness, what a busy looking table too. I'm having some sort of problem with my eyes there, flicking on me. I've only had, I think, maybe one or two what I would classify migraines in my life, and this is beginning to feel the light sensation like that. Not nearly as bad, so hopefully that's not coming on. Okay, we did x equal 1, and here we look at just a little bit greater than 1, 1.1, and here is the actual calculation of that. Okay, here's your linearization of that, plug it in. Well, you just had, so this is plugging in the linearization, this is plugging in the calculator. Why in the world they put up a table like this, I don't know. If you do this on the calculator, you get that. So you're off by, your error is less than 0.01. Pretty good. This time we got within 1/1000th of 1. Okay? Plug that in there, do this calculation, do the linear approximation of it, and now you're to 1, 2, 3, 4, 5, 6, within 10 to the minus 6 of your actual value. That is really good. 1 part in a million, basically, you're off there. But if you jump way up to 2.5, which is 1.5 beyond the 1 that you started with, not a good approximation at all. This gives you your linear approximation 3.25. Your actual calculation gives you 7 point. Yeah, you're way, way, way off there. 3.84. In fact, your error is greater than your linear approximation. Nowhere close on that. Okay. So that's your delta x is way too far from what your x value was. Okay. Now we've already done problems with this, but now they turn around and give you the formula for it. Your percent error formula is this one. Usually pretty easy to remember if you just think the percent error is the actual error, and usually this is plus or minus, but you don't do absolute values here, so it doesn't matter. Divided the actual error divided by the actual value, and then multiply that by 100 to give you a percent. Okay. So that was, the error was 10 to the minus 2 multiplied, we did one like this before. The error, how far off you are from the actual value, divided by the actual value times 100. That's your percent error. So that last one there, where you're further off, your error was actually greater than the, that was 3 point something, 7 point something. That's a miserable percent. Really, really bad. Okay. So let's look at example 6, which is not that one. So let's do it here. Goodness, I'm having trouble breathing. And I couldn't clear very much at all when I went down to the restroom. It just all clogged up in there. I think that has something to do with the eyes too. I hope I'm not getting a sinus infection or something. Here's what we're asked to estimate. Estimate the tangent, sorry, I can't talk, of pi fourths plus 0.02 and compute the percentage error. Okay? Estimate that. Wow. What is your function here? Hopefully it's pretty obvious. F of x here is Your function is the tangent function, right? Now, what your pi force is, that's your A. That's where you're evaluating it. And what would this part be? Delta x. Okay, very good. Okay, now, what's your estimate of what that would be then? Okay, I can't hear. Okay, so you're actually doing a calculation now, or? Okay, I couldn't quite hear. Tangent of pi force? Is that what you said? Okay, yeah. What is tangent of pi force? We should know that. Say again? 1. Very good. Okay. So we got this is be our f of A. Okay. What else do we need to do? One of those questions. Take a derivative. So f prime of x, we'll do it first to x, and what would that be? Say again? Yeah. Secant squared. Okay? But we really want to know that f prime at A, which is 1, which is, yeah, just a second, my head is so clogged up. Okay, now, I'm sorry, I said 1, a pi force. That's where we want to evaluate it. But what I want to do first is rewrite this as 1 over cosine squared. I like cosines far better than I like secants. Don't you? Say yes. Okay. All right. So what is that? What is 1 over, what's cosine of pi fourth? Anyone remember? Yeah, okay, it's the square root of 2 over 2. Now, let me take that back 1. That's the same as 1 over the square root of 2. No, 1 over 1 over the square root of 2. Right. I don't know if that's helpful or not. So, in other words, this would be, okay. I'm sure I'm getting you confused because I'm skipping too many steps. Let's do it fairly. Okay. Let's come off to the side and say, what is the cosine of pi fourths? And you said that's square root of 2 over 2. So what would be the secant of pi fourths? Well, secant is 1 over cosine, right? And this would just be the square root of 2. Because how you get square root of 2 over 2 is 1 over root 2, right? And so secant, since it's reciprocal of it, would just be root 2. We want secant squared, which would be 2. So this would be secant squared of pi fourths, which is equal to 2. Okay? Now, estimate this and compute the percentage error. Okay, so the estimate of this would then be sorry, the linear approximation at pi fourths would be f of pi fourths, which was 1 plus 2 times, okay, say that again. Okay, which is your delta x, isn't it? Yeah, that's the 0.2. Okay, so this would be approximately equal to 1 plus 0.4. This is approximately equal to 1.04. Okay? So that's our estimated value. We need to actually calculate what the actual value is. So if you got a calculator, do pi fourths, pi divided by 4, and add 0.02 to that, and then take the tangent of it. Pi divided by 4, that should give you a decimal answer. It's going to be something pretty close to 0.7576, something like that. And add 0.02 to it. Okay. Second, 0.02 to the pi fourths, and then take the tangent of that. Be sure you're in what mode? Radian. Everything in calculus pretty much is going to be in the radian mode if you're taking trig functions. What do you get? Second? Okay, say that one more time.
Pi over 4 plus 0.02 equals 0.805.
Okay. And then did you take the tangent of that? Yeah. I'm sorry? Yeah, the tangent of that value. That's what you're looking for. Okay. Pi fourths, I got to be point. Okay, maybe it is 0.8. I didn't know it was that large. $1.02. They got 1.0408. That's why I thought yours seemed a little. Okay. You did it on the calculator. I mean, on the computer. Okay. You got it. Okay. Well, I thought that number seemed a little further out than it should have been. So you got the actual value to be what? 0.0408. So your error here, or the absolute value of the error here, was 0.0008. So 0.0008 divided by the actual value 1.0408. Calculate that for us. Sorry. So the error was the difference between that and this. Actually, between this and that, it would have been a negative, but they're doing absolute values, so you don't have to worry with that. You get a decimal number? 768, and then multiply that by 100, and that would be a 0.08% error. Not bad. Not bad at all. Okay? Yeah, that's what we got. That's a pretty ugly percent sign. Okay. Any questions on that? All right. Examples in this section may have convinced you that the linear approximation yields a good approximation to delta F when delta X is small, but if we want to rely on the linear approximation, we need to know more about the size of the error. Okay? And here is Okay, sorry. After the flicking of my eyes, now the headache's coming on. This is not good. Okay. We've seen something pretty similar to this before. They may not have put this in. If this is your function, the blue curve is your function. The red line is your linear approximation to that function. Then the difference between the function and the linear approximation to the function is what we call the error, just like we were just doing. Subtract those two. Now, again, this is a function here, and now they've done the delta x several times bigger than what a was to begin with, which is rather bizarre to do that big. But that's why you got this much error. If you'd have done an error in this range, it's almost negligible, okay? If your delta x would have been pretty small compared to what a was, you would have almost a zero, not exactly, but almost a zero error, okay? So there's the graphical interpretation of the error of the linear approximation. All right. Well, those are going to be pretty tough to calculate precisely, but here they give you an error bound, and that's what this formula is. Okay. And it says in section 8.4, you'll prove that. That's not going to be in this course. This will be in Cal 2. Okay? Well, what is this K? What this K is your second derivative. Well, it is related to the second derivative. The K is the absolute value, the maximum value of the absolute value of f double prime in that interval from a to a plus delta x, okay? And you'll see this later when we do linear numerical numerical approximations of integrals. We have a couple of methods, and for each one we'll come up with an error method, and always generally relates to the second derivative. Okay, so that's what K does. K is the maximum second derivative value between a and a plus delta x. Okay, that you can have in there. Okay. Now, I tell my physics students this too. Quite often when you see the variable, here's its delta x here, raised to the second power, anticipate or expectancy of 1/2 in the coefficient. Here at D you have that. And the error bound is something in between that. It reminds me a lot of the acceleration part of a displacement formula. It has the same pattern there. Okay. What this error bound tells us, they say, are two important things. First, it says that the error is small when the second derivative and its K is small. What is second derivative measuring anyway? Second derivative measure. Second, rate of change of the first derivative. So in other words, if the first derivative is not changing very rapidly, the second derivative is quite small. So if the second derivative is quite small, then your error is pretty small because first derivative isn't changing much. So that's a really good approximation. Okay? So that's the first thing it tells you, okay? The second thing The error bound tells us that the error is on the order of 2 in delta x. In other words, the smaller your delta x is, then square that, and you get a really, really good error bound. So it's related to the square of that. But on the other hand, if your delta x is quite large, like larger than the a value to begin with, then you're multiplied by a number greater than 1 squared, and that actually gets a lot bigger. So you try to keep your delta x as small as possible. That gives you a good error. And if the function is not changing very rapidly, that gives you sorry, a good error, a fairly small error as well. Okay, a couple of illustrations of that first point is this. Remember, let's see, I don't think we use the term yet, so I won't say that. But here again is that fairly typical looking blue function we have. And notice that around A, the slope of that tangent line is not changing very much at all. So therefore, anywhere within this green circle, you're going to have a very good approximation, linear approximation, very small error there. But what if you happen to be right down here, and this is your a parabola here, and your first derivative is changing really rapidly here. So your first derivative here is negative, 0, positive, and more positive, stuff like this. Up here, it's not changing very fast at all, but down here, it's changing quite rapidly. So therefore, your error is going to be pretty large there, because your second derivative. When the graph is flat near x equal a, your second derivative is quite small. When the graph is bending quite rapidly near x equal a, your second derivative is usually quite large. Okay? The accuracy of the linear approximation depends on how much the curve is bending. And the other thing is that tells you something about the second derivative. And the other is delta x, how small your delta x is, because that quantity squared. Okay. And that finishes 4.1. To me, this part of the applications of derivatives, yeah, that's important, but to me, it's not the big deal. Okay. Do y'all want to do preliminary questions on this one? No. Okay. Homework exercises. Any of the odds 1 through 5. Do number 7. Any of the odds either 9 or 11 or both. Either 13 or 15 or both. Okay. Any of the odds 17 to 23, and any of the odds 27 through 37. Okay, I would do 39. It's sort of its own type there, so do 39. And then you get to choose any of the odds, 41, either 41 or 43, or both. Then any of the odds 45 to 53. Okay? Do either 55 or 57 or both. And any of the odds 59 to 67. Try to do number 69. That's the last one that I will say. And if you eat any more, then try to do any of the odds 71 to 75 if you choose. Okay. All right. Oh, these are repeats of some of the formulas or equations you ran into in the chapter. These are repeated in the summary, so that's why they're repeating them here. Pretty important thing, so I guess it bears repeating. If they repeated them, there must be a reason for it. I'm sorry, my eyes are just doing markers on me. All right, so reminding your change of f, this is your linear approximation. Your change of f is approximately the f prime of a times the change of x. Okay, it linearizes the derivative function basically, and gives you a good estimate of your if your delta x is small, a pretty reasonable estimate. Okay. The next one is if your delta y is approaching dy, which means that here we have a sorry. Man, I've got so much drainage I can really stand it. We were talking about the delta y in the previous one. That's approximately the same as the dy, as long as that dx again is small. Okay? Then combining those together, well, not really, but this gives us our linear approximation. And again, it's a lot like a point-slope formula. Your linear approximation minus alpha a would be f prime of a times x minus a. Okay? Usually that's going to be the case when you so basically all you need is sort of a rehash here. You have the function. You want a linear approximation. You have the function. Plug in the a for that. Take the derivative and plug in the a for that, and then write that derivative times the difference in x and a. You've got it. It's sort of like your delta x. And as long as your x is very close to some value, d, some permanent value, that gives you your function is approximately a linear function. Two things, as long as x is close to a, and the other thing is this function is not changing rapidly near a. If it is, it's not going to be a good approximation. And as long as x is pretty close to a, especially compared to how rapidly it changes. Okay. Now okay, finally discharge. Okay, let's go to 4.2. I should use another swig of water, but we don't have that much longer left, so I'm going to try to make it. All right. Now, to me, this is the big part of chapter 4. Your extreme values, and we're going to call them by several different names. And they start out with their approach on it. I don't know. Not how I did it with how it was put on. Maybe this is better, but this doesn't feel it comfortable. But here's just an example. Okay? I usually don't take much say, pain medicine and things like that. Usually I don't have headaches and things like this. But when you do, if you do take these, you notice when you first take it, it's not in your bloodstream. It's got to metabolize and get in your bloodstream. Now, that's not an immediate process, but it does start pretty quickly to increase because they're put together in such a way you do get in there pretty good. But you start feeling some relief within minutes, I would say. 15, 20 minutes, you'll start feeling some relief, but you get your maximum relief, in this case, right around 2 hours later, okay? And then it sort of tails off after that. And if it's sort of a chronic pain type situation, they usually have you take your second dose when? Yeah, about 4 hours afterwards. For some of them claim they're 8. In those cases, they probably are slower here, but then more gradual here. And then you might be able to go 8 hours. This one looks like one that they would probably have you take again at 4, because at 4, that second dose is going to come up like here, while this is decreasing, that's increasing, and you sort of level out your dose that way. Well, this may be one that you can wait till 6 or 8 because it's not tailing off too quickly. But especially if this was coming down pretty rapidly here, you would need to take a second dose in a certain number of hours. And this measures the drug concentrations in the bloodstream. I can remember a few times when I have had major surgeries. That's an important thing, and my wife was really good about keeping up with that, you know. When she was not there and I was keeping up with it, take the medication, then fall asleep, and then when I woke up, I couldn't remember when I took it before because it really knocked me out. So it was far better when she was there and say, no, you need to wait a little longer, or you should take it now because otherwise you're going to start hurting soon. So that gives it time to get back in. But this is an example of your maximum concentration in the blood. That's called an extreme value. Okay? Now, some of these terms here refer to maximum and minimum values, and they'll use max and min for short, as extreme values or extrema. Okay? Now all three of these words, maximum, minimum, and extreme, they're coming from, I believe it was the Greek, and the plural for those has an A at the end, not an S. So you have maximum, or if you have several maximums, they're maxima, okay? A minimum or several minima, extreme value or extrema. So that's sort of get used to sort of an unusual spelling and thing, but that's where it comes from. Now, when you're trying to find those extreme values, you're trying to optimize or do an optimization of your function. So here's our first definition here. What are these extreme values? Okay. All right. So let's picture this. You have some function here, okay? You have some interval that you're interested in that function, okay? The function's doing something, and you're interested on just some interval, and your A has to be in that interval, okay? Then we say that f of A is the absolute minimum of that function of f of x on that interval I if f of A is less than or equal to any other f of x you have anywhere in that interval. Okay? So let's say we have a function that does like that. And we're interested in the interval here. Right down there was the very minimum because every other value on here was greater than or equal to f of A. In other words, f of A was less than or equal to that. It's an absolute maximum on f of x on I if that f of a is greater than or equal to, can't be less than, any other f of x on that entire interval. That's the absolute minimum or the absolute maximum. Okay? Pretty straightforward concepts, I hope. Okay? And they say in the marginal note here, often we drop the word absolute and speak simply in terms of a min or max on the interval I. When no interval is mentioned, it is understood we refer to extreme values over the entire domain of the function. Again, you have to stay within the domain. Okay. Now, this sounds like repetition of what we've had before. Does every function have a minimum or maximum value? You would almost say, well, yeah, they have to. Not necessarily. Okay? And there's a couple reasons that may not be the case. And these pictures illustrate them. Okay? Goodness gracious, it's harder to focus. Okay. If your function happens to be discontinuous at right the wrong point, this is not, okay? For instance, here's your interval from A to B that's inclusive because you're including the A value and the B value. So this would be inclusive on A to B. Okay, that's how you write that. The bracket means you include the interval. Does this one have an absolute maximum? No, it doesn't. Okay? Now it looks like at x equals c, your absolute maximum could be 3, except it's not, because at x equals c, the value is at 2, not at 3. It seems like it should be going at 3. 3 would seem like it's the absolute maximum, but you see it never reaches 3 on that interval. It gets close but doesn't go there. Okay? So if it's discontinuous at what would have been the maximum value, then it doesn't have a max. Okay? Now this one looks like the minimum value is here, but it's not because that's an open. It's an open interval from A to B. Now B's got to be open, and the reason is it's going to infinity. It looks like that. It looks like a vertical asymptote. A, they just happen to choose that to be not evaluated there. On this open interval, there is no minimum, there is no maximum. Now this has a minimum down here at x equal A, that minimum would be 1. X equal B, it's greater than 1. X equals C, it's not 3. It looks like it could have been 3 if that would have been there, but they brought this down and made it 2 here. So there is no absolute maximum. You might say, well, is it something very, 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 very close to C? Well, give me something very, 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 very close to C, and then evaluate the value of that. I'll give you something in between that and C, and it'll be greater. So you cannot find a single value that would be an absolute maximum here. You do have absolute minimum, but not. This one, because it's an open interval here, and that would have been the minimum. If that had been a closed interval, that would have been the minimum value. Over here, no hope at all because it's going infinitely large. So that's an infinite discontinuity there and undefined value here. Now this one, no sweat. Starts here at A, doesn't give you any numbers over here, goes up, then comes down. The minimum is right there, the absolute minimum is right there, and then the maximum is up here. Okay? And here's what we say. Every continuous function on a closed interval A to B has both a max and a min on that closed interval. If it's not a continuous function like here, you're not guaranteed. It could have had one. If your discontinuity was right here and you were continuous there, then yeah, it would have been discontinuous, but it still have a max and min. But this one, the discontinuity happens right at one of those points, so it doesn't. Here it's an open interval, and this would have been your minimum, but it's open, so you get close to that, but never reach there. And if you do 8.000001, you're close to that, but you're not there because I could do 8.0000000001, and you would actually be less than at the other place. And no matter where you chose, I can always find one that's closer there. Okay? But this one, a continuous function on a closed interval, a to b, counting those endpoints. The minimum happens to be somewhere in the middle. The maximum happens to be one of those endpoints. And that's leading to the next kind of concept here. In fact, it's a theorem. Oh, man, my throat. Ooh, why did it do that? Oops. All right, I don't have a quite centered value. It's okay. Existence of extrema on a closed interval. Again, this is what we noticed in that third figure before. A continuous function. Notice that all it requires is continuity. A continuous function f of x on a closed, that means bounded interval. You count the endpoints on each one. I, from A to B, including point A and including point B, takes on both a maximum and a minimum value on that interval. Okay? Later we'll see. That the minimum and or maximum could either be one of the endpoints or some value in between. That's why you need the endpoints there, because if it's open interval, so it couldn't take on the value there, and that happened to be either a minimum or a maximum, would have been, then you don't have one anymore. So, all right. So let's talk now. We were talking about absolute extrema. Now let's talk about relative extrema or local extrema. Both terms are used. Now, we say that f of x has a local minimum at x equals c if that value, f of c, at that point, is the minimum value of f on some open interval in the domain of f, got to be in the domain of f that contains c. Okay? So in other words, this interval, local minimum, has to have values on both sides of it. Okay, basically. Minimum value of f on some open interval in the domain of f containing c. So it could be, c can't be the endpoint because it has to be an open interval that contains c. So c is somewhere in here, and you can go plus or minus from it. And if you do go plus or minus, this is the local minimum if you can't, if all the f values in that interval are greater than the value at c, f c, then that is a local minimum. Local maximum occurs at some other value alpha c if alpha c is the maximum value of f on some open interval in the domain of f containing c. So again, that's the local maximum. Here would be a local minimum. And they could take on other forms other than just the parabolic looking shape I was drawing there. Of course, people at home can't see what I'm fingering on the board. Okay, let's take a look at these. Okay. All right. Now, they give us a function here. They don't give us an interval. That's okay if they don't give us an interval. You assume it's everywhere the function is defined. Certainly seems to be defined everywhere there, so we're going to assume that. Okay? Now, if indeed it's just this graph here, then this would be your A and that could be your B. Now, to be a local minimum or maximum, you've got to have points on either side of it, some open interval around the point. And around that point here is the open interval. And that's the local minimum. If no other point close to that can be a smaller value, that's the local minimum. Local max is that for some interval around that point C, then the alpha of x is within that domain, that limited part of the domain. None of those alpha x's can be greater than that alpha c. Okay? Over here, the same thing, a local minimum. Definitely not the absolute minimum. That would appear to be the absolute minimum. But this is a local minimum because on the points near that value of x, d say, points near d would be all greater than, the alpha value would be all greater than alpha value at d or whatever. Now, let's now put this same graph in an interval. Okay? This interval is going to start at A here, and there's your alpha of A, and go to B here, there's your alpha of B. So we're going to lose some of this and some of that. Okay? If it's on that interval, then what is your absolute maximum? At A, because none of these other values in that interval is as large as A. Local maximum would be right here. This is not a local maximum, believe it or not, because the local maximum has to be in an interval around that, and since this is on the boundary, you can't be anywhere around that. This would be outside of that, and this would have greater value. That is a absolute maximum for this function, because that's the absolutely largest value within the interval. This is a local maximum because it does have values in between. I mean, values on either side that are all less than the value of C. Now, this has two local minimum here and here. At B, you have nothing. Nothing of interest. It's not a local maximum. It's not a local minimum. Okay. It's not local anything because it's at the boundary. For it to be local, it has to go either side of that boundary. So it's not an absolute either because this value here is less than that, and this value is that and greater than that. So yeah, it's not an absolute maximum or minimum. But you always evaluate the endpoints and see if they are an absolute maximum or minimum. Local minimum here, another local minimum there, local maximum there, absolute maximum there. This local minimum happens also to be an absolute minimum for that interval, or that interval. Okay. Now, man, oops, if I'm not mistaken, we just hit the witching hour. My throat is not too sorry that we did. So we will start next time at this. This is near the top, not right at the top, but near the top of page 202. Now, I don't think anyone else came in. Everybody did get a copy of the second test. Good deal. All right, we will. This chapter is not nearly as long as the previous chapter. So we've already done one section. I say that, but let me just look and see. Actually, it is fairly long, but we're not going to do every section. So we should finish this fairly quick. We'll see you on Wednesday. Good deal.